Hello everyone, this is Mrs. T for Mrs. T's Chem Talk for Regents Review. This video will be for the January 2017 exam, questions 31 to 50, which is actually part B1. I will explain all of those questions. It's a good idea for you to have that exam already completed and to take that exam out and look along with what you've put for your answers and your work as I'm doing this with you. For anyone who doesn't know me, my name is Mrs. T, and I'm a chemistry teacher at Calhoun High School in Merrick, New York. So in my class, we call this the Violet exam, but this is January of 2017, and again, we're going to go over questions number 31 to 50. So the first question says, which electron configuration represents the distribution of electrons in the potassium atom in the ground state? We said that for our different elements, the periodic table has the electron configurations for the ground state. So what we're actually going to do, we are going to switch over screens and we're going to look at the periodic table and we're going to find potassium. In case you don't know the symbol for potassium, you can also look on reference table S. And on reference table S, when I find the element that we're looking for, which according to the exam is potassium, we're looking for the word potassium, and I see it right here, and I see that the symbol is K, and the atomic number is 19. So I'm going to switch back to my periodic table and look up the element with the atomic number of 19 and the symbol of K. Now, according to my key here, the electron configuration is found at the bottom left-hand corner of each of our boxes on the periodic table. And so the ground state electron configuration for potassium, if I copy it, is 2-8-8-1. And what that means is that there are 2 electrons in the first energy level closest to the nucleus, and there is 1 valence electron in the outermost shell. So 2-8-8-1 is right here. These are the ground states. Now this 2-8-7-2 can represent an excited state, and what that means is that one of these electrons moved further away from the nucleus. Electrons absorb energy to get into the excited state, and when those excited state electrons move back down to the ground state, they give off light. And that's how we get the color in fireworks. That's how we get the color in the flame tests. And if we separate that color with a prism or another item called a spectroscope, we can actually get the bright line spectrum, and we can identify elements based on their bright line spectra. When the question asks which conductor is malleable and a good conductor of electricity, these are 2 of the properties of metals. Remember that besides malleability and being good conductors of electricity because of their mobile electrons, metals are also ductile, they are shiny, they have luster, they have low electronegativities, which means they lose electrons more easily. They have low ionization energies also, which is another property that tells you that they lose electrons easily. When we look at the periodic table, Our metals, remember, are the elements that are found over here, as well as down at the bottom. So remember that as we look at the periodic table, that hydrogen is a nonmetal, but that all of these elements, including the elements at the bottom, are metals. And when we look at the periodic table, the element that was on that side was platinum. And again, remember that if you don't know the symbols for these elements, you're going to look them up on table S. And when you look at table S, you can look up the symbols versus the names for most of the elements. Which general trend in atomic radius and electronegativity are observed as the elements in period 3 are considered in order of increasing atomic number? Well, we're going to look at period 3, and remember that when we're talking about periods, we are talking about the horizontal rows. Members of the same period have the same number of shells of electrons, but they're very different from each other. So as we go across a period, what we tend to see, because of this increasing number of protons as we go across, we also call that an increasing nuclear charge. What we see is that as we go across, the atoms tend to get smaller and smaller. Remember, they have the same number of shells of electrons, but having more positives in the nucleus pulls those valence electrons and all the other electrons in closer to the nucleus. And by having a stronger pull or a better hold on the electrons, we're also increasing the electronegativity, which means that they're holding on to them more tightly. And we're increasing the ionization energy, which means that it starts to take more energy to remove those electrons, those most loosely held valence electrons. We can also look on table S, and we can compare Na, Mg, Al, Si, right? Because those are the elements as we go across period 3. And if we want to, we can also switch to table S, and we can find Na, Mg, Al, Si, and P. And remember, we can look up the ionization energy, the electronegativity, the melting point, boiling point density, and atomic radius on this chart. So as we go back, what we were looking for on this, we were looking for what happens to the atomic radius and electronegativity. We said that as we go across a period, the atomic radius tends to decrease and the electronegativity and ionization energy tend to increase. For number 34, we want the chemical name for Na2SO3. We said that if we have more than 2 capital letters, you're going to check table E to see if part of it is on table E. And if part of your compound is on table E and the other part is a metal or a nonmetal or something else from table E, that compound has both ionic and covalent bonds within it. So we are going to look on table S for the name of Na. And when we look at table S, this has been a lot of table S work. When we look at table S, Na is called sodium. So the first part of the name is sodium. The next place that we're going to look for the other half or the other part of the compound is table E. and I'm going to try to find SO3, and it says on table E that SO3 with a -2 charge is called sulfite. So we're going to call this sodium sulfite. The reason why we don't change the name of the sulfite, anything on table E will automatically just keep that part of the name. That part of the name that's on table E never changes. And the reason we wound up with Na2SO3 is because the sodium on the periodic table has an oxidation number of +1. If we look at it right here, it has an oxidation number of +1. And on table E, the sulfite has an oxidation number of -2. So if we go back and we put in the Na with a +1 and the SO3 with a -2 charge, and we crisscross and drop the signs, we get Na2SO3 for sodium sulfite. Which molecular formula is also an empirical formula? Remember, molecular tells us exactly what is in the molecule. The empirical is the reduced form of the formula. So C6H6 can still be further reduced because we can divide by 6 and get C1H1 or just CH. H2O2 is also not reduced because we can divide by 2 and just get O1, which would be an empirical formula of HO. N2H4, we can divide both subscripts out by 2, which would give us N1H2 or NH2, and N2O5 is already as reduced as it can be. For 36, this question is going to be a question that is about the law of conservation. If things react completely, the total mass of your reactants has to equal the total mass of your products. So these are my reactants. Remember, we said that the arrow can also be represented with an equal sign, because for our reactions, our total mass of reactants and our total mass of products have to be equal if we have a complete reaction. So if we do 4 plus x equals 36, x equals 32, because we had to add 4 grams to 32 grams to get a total mass of 36 grams of product. For number 37, to find the gram formula mass, remember this is also the mass of 1 mole. And what we're going to do is Ca's mass on the table times 1, and then the O and the H, because they are in parentheses, this too multiplies by each of them. So we're going to take the masses on the table and multiply by 2. Now, I know in my class we always did everything to the nearest tenth for gram formula masses, but these are all to the whole number. So I'm going to round from the periodic table to the whole number to do my work here. When we look at the periodic table, we're going to find the masses of these substances or these individual elements. And as I said, I'm going to do this to the nearest whole number. So calcium is 40, which times 1 is 40. Oxygen to the whole number is 16, times 2 is 32. And hydrogen is 1, which times 2 is 2. When we move back over to our other screen and do the math, we wind up adding these different numbers up, and when you add 40 and 32 and 2, you wind up with 74. So 74 grams of calcium hydroxide will be 1 mole of calcium hydroxide. For number 38, it says which statement describes the energy changes in this reaction. We have H2 and I2, which means that the H is connected or bonded to the other H. The I is bonded to the other atom of I. And what we're making is 2 molecules, or 2 moles, I should say, of HI. And the HI also has a bond in it. So we are breaking the reactant bonds and we are making the bonds in the products. We said that we have an acronym that we can use, and it's called BONDS, BARF. When we break a bond, energy is absorbed. We release energy when a bond is formed. So energy is absorbed as bonds are broken, released as bonds are formed, because we're breaking the bonds in the reactants and making the bonds in the products. For number 39, it says, based on table F, which compound is least soluble in water? When they say least soluble according to table F, it's basically going to be the one that comes out as insoluble on table F. So let's just switch over to table F. And so we are looking for which element is insoluble. And if we look at table F, we actually need to use both sides of table F. You always want to look at both sides. So for AlPO4, I'm going to look up aluminum in the first column, which I can't find it. And then I'm going to look up PO4 in the first column, which I have PO4 here. For calcium hydroxide, I'm going to look up calcium in the first column, and then hydroxide in the first columns, which I have here. For AgC2H3O2, which is silver acetate, I'm going to look up silver in the first column, and then acetate in the first column, which is here. And Li2SO4, lithium sulfate, I'm going to look up lithium in the first column, and sulfate in the first column. So aluminum phosphate was our answer, so I'm going to actually do that one last. If we look at calcium hydroxide, hydroxide is generally insoluble, but calcium is an exception. If you have both something from the first column and something from the second column, that negates the top. So that means that calcium hydroxide is soluble, and the question asked us which one is insoluble. So that can't be the soluble answer. If we look up silver acetate, acetates are soluble with no exceptions. So we have just the first column, so we keep the heading. So this is also soluble. Lithium sulfate has sulfate without its exception, which means that it is soluble, and lithium, which is soluble with no exceptions. So soluble with no exceptions means that one is soluble. Now let's look at aluminum phosphate. Phosphates are generally insoluble, and aluminum is not in group 1. Aluminum is not ammonium, which means that we keep this heading. So if you have just something from the first column, you keep the heading. If you have something from the first column and something from the second column, you negate the heading. When we look at number 40, the question asks us how many joules of heat are absorbed to raise the temperature of 435 grams of water from 25 degrees Celsius to its boiling point of 100 degrees Celsius. If we are raising the temperature, that means there is a change in temperature. That means we're going to use the formula that has delta T in it. So let's take a look at table T, and let's see what formula we're going to use. When we look at the heat formulas, the one that is for a change in temperature is Q equals mc delta T. That means we're going to have Q for the heat, which will be my X, M will be the mass, C will be the specific heat capacity, which we will look up on table B, and delta T will be the change in temperature. So table B has the specific heat capacity, heat of fusion, and heat of vaporization if we're talking about water. So if we switch to the front of the reference table, to table B, we see that if we're talking about water, we have the heat of fusion, which is for melting and freezing for the phase change, heat of vaporization, which is for boiling or condensing, which is another phase change, and specific heat capacity, which we will use when there is a delta T. So heat of fusion is with Q equals MHF. Heat of vaporization is with Q equals MHV. Specific heat capacity is 4.18 joules per grams times Kelvin. When we look back at our question, it says that the mass, we're looking for the Q or the heat, the mass is 435 grams, and the delta T is going to be 100 minus 25, which is equal to 75. Now I switched the Celsius to Kelvin because the difference between two Celsius temperatures will be the same as the difference between two Kelvin temperatures. So now in chemistry, when the Regents chemistry anyway, if you have the same unit written twice, you can cancel it out. So 2 Ks, 2 Gs, which means my final answer comes out in J or joules. I plug in to the formula. And when I multiply out, this is the number that comes out of the calculator. So 136,000 can round to 140,000, and then remember to go from joules to kilojoules. I'm sorry, we don't need to go from joules to kilojoules. To go from regular notation with a floating decimal to scientific notation, we count the number of decimal places. 1, 2, 3, 4, 5 places to get one digit in front of the decimal. That's why it is 10 to the 5th. For number 41, when we're talking about average kinetic energy, that is measured by temperature. But we need to have the values in the same temperature scale. You can't compare Celsius to Kelvin. We're going to need to convert somebody. I prefer to convert Celsius into Kelvin since we try to usually use kelvins in most of our math formulas that require temperatures. On table T, we have a formula that says K equals degrees C plus 273, and again, this is on table T. When we switch back to the question, if we add 273 to our 2 Celsius temperatures, we can find out what Kelvin temperature each of them represents. When you add 27 plus 273, this one is equal to 300 kelvins. When you add 12 to 273, that one is equal to 285 Kelvin. And now we can compare these 4 Kelvin temperatures, and the one that's equal to the highest temperature would be the highest average kinetic energy. The next question asks which change in the H plus ion concentration of an aqueous solution represents a decrease of 1 unit on the pH scale. So our pH scale tends to usually be given as 0 to 14. We can go higher than 14 and lower than 0, but for our purposes, usually we're between 0 and 14. Remember that 7, when at room temperature, represents a neutral solution where the concentration of H plus is equal to the concentration of OH minus. Remember, all solutions have both of these ions. It's their ratio that determines whether the solution is basic, where the OH minus is greater than the H plus, and the higher we go on the pH scale, the more basic we get and the more OH minus we get. The lower we go on the pH scale, the more acidic we get, and the higher the ratio of H plus is to OH minus. So down at the lower pH, we have more H plus and is more acidic. At the higher pH, we have more OH minus and more basic, but we always both have each kind of ion. Remember also that the pH is equal to the negative log of the H plus concentration. That's what this P means, negative log of H plus. So the lower we go on the pH scale, the more H plus. Every number on the pH scale is 10 times more. So every number on the pH scale is 10 times. So if we want to know about 1 unit of the pH scale, it's 10 times. If it was 2 units on the pH scale, would be 100 times difference. 3 units on the pH scale would be 1,000 times difference. Remember, it's the number of zeros that can tell you how many places you want to move on the pH scale. So if we want to decrease 1 unit on the pH scale, we're changing by 10 times. As we go down on the pH scale, it's more H plus. So it's a 10-fold increase of H plus going down 1 place on the pH scale. For number 43, it says which diagram represents a mixture of 3 substances? Now on your picture, number 3 and 4 are over here. So 3 is here and 4 is here on your picture. We want 3 substances, so we want 3 different kinds of molecules. And a molecule is going to be the same type of connected atom. So in this one, we have 1 molecule and 2. So this only has 2 substances. For B, we have this is 1 type of substance, both open circles with connected in 2s. This is a second type of molecule, closed circles connected in 2s. And this is a third type of molecule, which is 1 open, 1 closed. Here we have 1, 2 substances, and here we have 1, 2 substances. So these are all mixtures because they contain different kinds of molecules, different kinds of connected atoms. But 1, 3, and 4 have 2 substances each. B, or 2, has 3 substances because it has 3 different kinds of molecules. For number 44, it says that the system is at equilibrium, and we said that reversible reactions in closed systems can reach equilibrium. And once we reach equilibrium, we have equal rates of the forward and reverse and constant concentrations of reactants and products. So we're looking for the choice. So concentrations are constant. Rates are equal. Concentrations are constant. For number 45, it's asking us if we're talking about this compound, this formula representing a compound. What is the IUPAC name? Remember that you don't need to know what IUPAC stands for. It's just the way we name things. It's the people who come up with the rules of naming. And according to the IUPAC, we first find the longest chain of carbon atoms. We can use table P for the prefix. And when we count the number of carbon atoms in this chain, we have 1, 2, 3, 4, 5, 6, 7 carbons. And those carbons have single bonds. So when we look at table P, 7 carbons represents or is represented by the prefix hept, hept 7. Then we're going to look at table Q and see that when we have single bonds only, we're going to be an alkane. Now alkanes end in ane. Single bonds, alkane ends in ane. Now the next thing we're going to do is identify our groups, our branches. The H's are not part of branches, but these two Cl's are branches. So we're going to need to give those branches a name and a location. So when we get our location, we count from the end that they're closer to. So they're sort of closer to this end. So 1, 2. This is the second carbon for this branch and the second carbon for this branch. Because these are not hydrogens or carbon groups, this now needs to go to the functional group table. So we're also going to look at table R. And on table R, Cl is called chloro. So this molecule is called a halide or a halocarbon. So if this is a 2-chloro and this is a 2-chloro, we're not going to say 2-chloro, 2-chloro. We're going to say 2,2 and use the prefix di, which means that there are 2 chloro groups. They're each on the 2. Each group needs to have its own number, and there are 2 groups, which is why we get the di. So 2,2 dichloroheptane. Even though 1, 2, 3, 4, 5, 6 from this end, we always use the smaller set of numbers to identify the location. So these are the location. This is how many. And this is the name of the branch. And then heptane is the name of the parent chain. Remember, we always have our last name relating us to our parents. For number 46, it says, given the reaction representing giving the equation representing a reaction, we see that the tin's oxidation number is changing from +4 to 2. And if we put these on a number line, +4 goes lower on the number line to get to +2. If it's easier for you to see it on a vertical number line, we have to have the charge go down to get to +2. If that's the case, we said that in oxidation reduction, we use GER down and LEO up. So gaining electrons is reduction and the charge goes down, losing electrons is oxidation and the charge goes up. This charge was going down, which is why we label it as reduction. So for 47, it says which ionic equation represents a spontaneous reaction that can occur in a voltaic cell. So we said that for a voltaic cell, it's spontaneous and happens without any help. It's the nature of the reactivity of the metals that makes the more active metal the anode in a voltaic cell. And we also know that the anode is oxidation. So we have to find out which of these reactions shows the more active metal on table J being oxidized. So first of all, A, copper and zinc are both going up from 0 to +2. That's 2 oxidations. And that doesn't happen because for a redox reaction, both reduction and oxidation have to happen at the same time. For B, copper is being oxidized because its charge is going up. Zinc is being reduced because its charge is going down. In choice 3, copper is being reduced because its charge is going down. Zinc is being oxidized because its charge is going up. And in D, both copper and zinc are both being reduced, which again, for a redox reaction, both oxidation and reduction have to happen at the same time. So we're going to look at table J and we're going to say, is Cu, copper, or zinc more active? And then we're going to come back and look and see what the results are of what we checked out. So we want to know, is copper or zinc, which one is more active? And when we look at table J, we want to see, should copper be the one that's oxidized or should zinc be the one that's oxidized? So looking at table J, we said that the more active metal should be the one that's oxidized. Here's zinc, here's copper. Zinc is the more active metal. So since zinc on table J is the more active metal, zinc is the one that should be the anode, and zinc is the one, since anox, zinc is the one that should be oxidized. That's why C is the answer. Just a few more questions and we'll be done with this part for this video. There will be another video. There are actually 2 more videos for the Violet exam. There's one video for numbers 1 to 30 and another video for 51 to 85. So when we look at number 48, it says, given the formulas representing 2 compounds at standard pressure, these 2 compounds can be differentiated by what? So propanol has 1, 2, 3 carbons, and methyl ethyl ether has 1, 2, 3 carbons. This has 1 oxygen. This has 1 oxygen. And if we count 1, 2, 3, 4, 5, 6, 7, 8 H's and 8 H's. So these 2 molecules have the same molecular formulas. They have C3, H8O1, but they have different structural formulas. And anytime you have the same molecular formula, but different structural formulas, they are isomers. So they are isomers, but they have the same number of hydrogen atoms, the same gram formula mass because they have the same formula, and the same formula will give them the same percent composition by mass of carbon. But because of their different structures, their boiling points are going to be different. Here, we have the oxygen connected to a C, or actually connected to two C's. Here, we have the oxygen connected to an H. So where this molecule has only dispersion forces, this molecule has dispersion forces and hydrogen bonding. And since hydrogen bonding is stronger than the dispersion forces, this will have stronger intermolecular forces overall, and stronger intermolecular forces will give you a higher boiling point. These also have different sets of functional groups because this is an ether and this is an alcohol. And remember, those functional groups from table R give us different properties for the different types of molecules. For number 49, it says that the table below shows the atomic mass and natural abundance of two naturally occurring isotopes of lithium. We said that when they talk about atomic mass, natural abundance, and naturally occurring isotopes, we are talking about finding the average atomic mass. These different isotopes have the same number of protons, but different numbers of neutrons, which gives them different masses. We are going to take the mass times the percent and get a number, the mass times the percent and get another number, and we're going to add this up. And we can either do this by writing the actual percent sign, so 6.015 times 7.6% and then getting a number, 7.016 times 92.4% and getting a number. We can move the decimal back two places, which would be 0.076 or 0.924, multiply like that, so 0.076 and 0.924 times the masses, and when you add those two results up, you'll get the atomic mass. Or, as a third method, we could do the percent and multiply by the percent and then put the whole thing over 100 and add those two numbers together. So in option B, they moved the decimal back two places. 7.6% becomes 0.076. 92.4% becomes 0.924. When we take into account both the mass and percent abundance of the naturally occurring isotopes, we get the average atomic mass. And finally, for the last question on this particular review video, again, there are two other videos going over the Violet exam on my Mrs. T Chem Talk. Feel free to share this with anyone else who you think might want to see it. You can also subscribe if you want to have information and be able to access this more easily for other Regents Review and AP Chemistry videos. This equation representing a reaction at equilibrium. According to one acid-base theory, why is this an acid-base reaction? So remember, when they use this term, one acid-base theory, or sometimes they'll say another acid-base theory, we're talking about the Bronsted-Lowry theory, and that's the theory that goes with H plus bad. For this alternate or other acid-base theory, for bases, they are acceptors, acids are donors. So it's H plus, bases accept, acids donate. So they're asking for somebody to be a donor and an acceptor of H plus. Now you're going to have one one donor and one acceptor on the left, and one donor and one acceptor on the right. The way that we identify is by connecting something from the left to what it looks like on the right. So these each have S's, and these both have CH3. The one that has more H's can act as the acid donor. The one of the pair that has less H's can act as the base acceptor. So NH2, NH3, this is more H's, that's the acid donor. NH2 is less H's, that's the base acceptor. So H2S is an acid donor. CH3NH2 is a base, which is an acceptor. So again, this concludes the Violet exam, Mrs. T Chem Talk review for numbers 31 to 50. There will be, or there is another video for 1 to 30, and there will be a third video for 51 to 85. You can find these on Mrs. T Chem Talk YouTube channel. So if you just Google Mrs. T Chem Talk YouTube, you should be able to find my other videos. Good luck studying.